So remember the Pauli exclusion principle. We've been talking about one electron at a time. What happens when you have more than one electron in an atom? According to the Pauli exclusion principle, no two electrons can have the same four quantum numbers. And those are the principal quantum number, angular momentum, magnetic, and the spin. Why? Has some really deep math relating to symmetry and spin. What is an electron? Very complicated physics there, but it turns out because we're just going to accept that now. And so in practice, once one orbital has two electrons, one of each spin, there is no room for another electron. Although it's a low energy orbital, another electron simply can't fit there no matter how low energy it is. It must take a higher energy orbital. And that's the key point here, is that you'd think that they'd all love to be in the lowest energy state, but they can't. They have to take the next available room. Great. So that's the principle we're going to use to put this all together. So some terminology here. Electron configuration is a description of which orbitals are occupied by electrons. How are the electrons arranged in their orbitals? Degenerate orbitals, those are orbitals that have the same energy level. For example, the 3p orbitals in a given subshell. Those are degenerate energy levels. Although the 2p are always higher than the 2s, all of the 2p's are at the same energy, at least before you put any electrons in. Things, things get a little more complicated once you start adding something to one of the 2s. Then the other two are a little different from that first one. But before you put any electrons into any of the 3p orbitals with ml equals -1, 0, and 1, they're exactly the same. Those are still degenerate. The ground state electron configuration is the lowest energy configuration. Remember, in all of this in the next lecture too, we're going to be talking about the ground state. We know, just from learning about the Rydberg equation, that electrons can jump up and down between energy levels quite a lot. And that does happen quite a lot. But at room temperature, most of them spend most of the time at the ground state. So most of the reactions we see will be determined by the behavior electrons in the ground state. And finally, the Aufbau principle, I've used that word several times. It's a German word meaning building up. So it's essentially the rules for determining the filling order of orbitals. As we build up, as we add electrons on, we build them up. For each element we go to, we're adding one more electron. And these are just the rules for building up electron configurations from no electrons to completely fill. Okay, so what are the rules of the Aufbau principle? So lower energy orbitals fill before higher energy orbitals. This makes sense. An orbital can only hold two electrons, which must have opposite spins, the Pauli exclusion principle. If two or more degenerates of orbitals are available, follow Hund's rule. So what's Hund's rule? So Hund's rule is if two or more orbitals with the same energy are available, one electron goes into each until all the orbitals are half full. So you don't crowd two orbitals at once. You put them into each degenerate orbital one at a time. If you've got 3p orbitals, you put one into the px, one into the py, and one into the pz. A way to think about this is, electrons are repelling each other. So you wouldn't put two in the px because then they'd be closer together, right? The px is shaped like this. If you put two in this orbital, they're close to each other. They'd rather go into the py orbital or the pz orbital, which doesn't overlap very much. So Hund's rule is first we fill up the orbitals halfway, and then we fill them up the rest of the way. And it turns out that because of the spin interactions between electrons, the electrons in the half-filled orbitals all have the same spin. It's a little lower energy to be in an orbital to have all of the spins the same than to have them different. Again, the energy levels are not big. You can get the spins to change a little bit, but at the ground state, you want to have all your spins paired up. You want to have them all parallel in the same direction. That's lower energy than having spins that are opposite. Okay, so that's it. That's all we need to know. There's a couple things we have to worry about where the energy levels between the 3D and the 4S change a little once they're partially filled. But we'll get there in a second. There's not that many. Almost everything can be explained with just those principles. So we start out. And so here, like the biggest thing is just getting the terminology right. So hydrogen has one electron in the 1s orbital. So that 1 in the exponent, it's not an exponent. It's to indicate how many electrons in the orbital. It's not s to the 1. It's 1s electron. So 1 electron in the s orbital, of course, because L equals 0, that's s, and there's only 1 there. Next, we got helium. So helium has 2 electrons. They're both in the s orbital. So we put it as a little superscript to the s. It's not s squared, it's 2s electrons. But we're still at n equals 1. We're still in L equals 0. Next, lithium. And now that we're adding electrons in another orbital, we do it from lowest energy to highest energy. That's convention. I mean, you could easily do it the other way around, but the convention is lowest to highest. So now we're adding an electron in a new orbital, so we have to write that orbital down too. 2s, there's 1 electron in that, 1 in the superscript. Not a power, superscript. Let's skip ahead a little. Now to nitrogen. So we have 2 electrons in the 1s orbital, 2 in the 2s orbital. Next highest orbital in energy is the 2p. So there's 3 in the 2p, not p to the third, just 3 electrons in the p orbital. And another way of looking at this frequently is an orbital filling diagram that contains the same information, but it's a little more, well, there's a little bit more information there, as you'll see, because it also shows the spins. So for orbital filling diagram, then we write the orbital down below, we have a little line, and then we put the electrons above the line. So 1s, 2s, in order to have 2 electrons in the 2s orbital, we have to show the spin down as well. So that's what the orbital filling diagram also has. It has information about the spin as well. 2s, and here's one question, does it matter if you only have 1 electron, does it matter if it's up or down? And that's actually essentially arbitrary, spin up, spin down. So could they all be spin up? They could all be spin down. Usually people, just as a convention, write spin up in there. What really matters when you're comparing multiple electrons together, then it's important what their relative spin is. So that's 2s. Yeah, let's see, and let's keep, am I missing? Well, let's draw in. I don't have nitrogen there, but let's draw. So we've got 1s, 2s, and then we've got 3p. So we have 2 in the 1s, 2 in the 2s, and then 3 electrons in 3p. And so they're all in this, have the same, they'll have the same, the spin that's parallel to each other. They're all spin up here. Difference between spin up, spin down, it's essentially arbitrary, but they all have spin in the same direction. Okay. So let's go on to, so now you can imagine that this gets to be a pretty big pain once you're dealing with 50 electrons or so. You don't want to have to write out all the 2s, all the 3d, all the 3p. So you have a condensed or noble gas shorthand configuration. So neon, we've got 10 electrons, the 1s, the 2s is full, the 2p is full. We just write that in brackets neon. So because we've got essentially all of the second shell in there. So we'll just say, yeah, the second shell is complete. That doesn't change very much. Once we start moving on to the third shell, we'll put it in the end in brackets. And then so sodium, which is 1 more electron than that, we write as neon with 3s1. Phosphorus, which you can see all the electrons there, would be neon 3s2, 3p3. Potassium, now we're getting all the way up to the 4th shell. So the 3rd shell is completely filled. So we're going to write that as argon with 4s1. So you should be familiar with both of these. But usually once you're, trying to get some real work done, then you'd be just use the shorthand configuration. Less time. Scandium. Scandium would end up being argon 4s2, 3d1. So this is how, everything gets filled. So what we do is first we fill in the S, S1, the 1s, and now helium, it's sort of over here because it's weird because it's both completing a shell and it's just S electrons. So you could say, should helium really be over here? Well, that's sort of arbitrary, but we've chosen to put it there with the noble gases, that you fill a row once you complete the shell. So, and then the 2s get added here. And then, we don't fill any d orbitals. That building up, we still have the 2s, the 2p, then the 3s, the 3p, the 4s, and only then do we get to the 3d. And then after the 3d, we go to the 4p. And so you sort of have this offset, here's the 5s, and then there's the 4d, here's the 6s, and the 5d, here's the 7s, and the 6d. So the s's line up with the p's, the d's are always one behind. And then, of course, the f's, strangely enough, get added in right in there between the after lanthanum and after actinum. They get added lanthanide, and after actinum they get added right in. So 57 jumps to 58. You do all 14 there with the f electrons. And which f electrons are these? They're going to be the 4f electrons. The 4f electrons start on the same row as the 5ds and the 4s's. F electrons, they're just crazy guys. So we don't worry about them too much because these are all very rare elements. If you're dealing with, radioactives, then you got to deal with them. But in most cases, we won't in this class. Okay, so in order to determine the electron configuration, you literally just have to read off the periodic table. You know where exactly the S's are being added, the D's are being added. So if you know the element, you can look up in the periodic table and just write the electron. So if we remember these blocks, we remember the F block, the S block, the P block, the D block, we can simply read off the periodic table and know exactly where we are in building up the electron.